Now we will analyze the case when the magnetic field is applied along the direction of the sublattice magnetizations. As you can see here, in the previous case we had a transverse situation, magnetic field was applied perpendicular to the sublattice magnetizations. Now it's in the longitudinal direction. And as a result of that, what we see is that before t equals 0, we had MA and MB equal to each other, balancing each other. A sublattice was feeling a Weiss molecular field gamma MB pointing in plus z direction, and B sublattice was feeling gamma MA pointing in the direction of its magnetization. For t greater than 0, when I turn on a magnetic field in the direction of the A sublattice magnetization, the magnetization of the A sublattice increases to M sub A plus delta MA, and the B sublattice magnetization decreases to M sub B minus delta M sub B. And now the Weiss molecular field acting on the A sublattice also changes, gamma MB minus delta MB, and on the B sublattice also changes, gamma MA plus delta MA. Okay, so basically we see that the effect of applying the magnetic field in the direction of MA is to increase it to a value MA plus delta MA and decrease the MB to MB minus delta MB. The external field is applied in the direction of MA opposite to MB. As a result, MA increases to MA plus delta MA, and MB decreases to MB minus delta MB. So we expect to see a net magnetization in the direction of the applied field. Okay, so what is this net magnetization? Well, it will be equal to the new A sublattice magnetization, MA, so let's make sure this is a positive number, absolute value of delta MA, minus MB minus delta MB. So if I open this up, this will be MA plus delta MA minus MB plus delta MB, and since I have MA equals to minus MB, there will be a cancellation here. MA and minus MB will disappear. So we will have delta MA plus delta MB. MA minus MB is 0. So these are the absolute values. MA vector is equal to minus MB vector, but in magnitude, MA is equal to MB. So the magnitudes will cancel each other, and we will have delta MA plus delta MB as the net magnetization. So we will have the net magnetization magnitude equals to delta MA plus delta B. Okay, so let's see the situation in the magnetization versus alpha plot. So here you have magnetization of the A sublattice or magnetization of the B sublattice. So let's plot the magnitude of A or B magnetization as a function of alpha, and at the beginning at alpha 0 where we have zero magnetic field, this is where we have the magnitudes of MA and MB being equal. Now the effect of applying a magnetic field is to increase this alpha value. Alpha, remember, is mH over Boltzmann constant times temperature. So when I increase the alpha value, the MA will increase to MA plus delta MA. So this will be the new value, the value at alpha 0 plus delta MA. On the other hand, the B sublattice magnetization decreases to MB minus delta MB. So that's because we have the absolute value plotted here. You can see that increasing the value of alpha has the effect of shifting to the left in the B sublattice because it's the minus M sub A, so we have a minus sign, therefore it shifts in the negative direction. Okay, so if you put a line here at point alpha 0, you can see that the slope of this line will be equal to roughly delta MA over delta alpha for small magnetic fields that we apply. Okay, so what I'm going to do is I will assume that even though this curve is not symmetric or it's not linear, the changes in the A and B sublattice magnetizations may not be the same. I will assume that I have a small enough magnetic field that doesn't cause too much asymmetry here. So for simplicity, let's assume that the applied field produces equal changes in the two sublattices. So this is my assumption. So with that, I will have magnitude of delta MA equal to magnitude of delta MB, or I will have delta MA vector will be minus delta MB vector. So we can write it this way. And that will give me, for the net magnetization, M net, remember it was delta MA plus delta MB, this is going to be equal to twice delta MA. So this will be by net magnetization, twice the change in the A sublattice magnetization. So I call this point P. If I look at the slope at point P, is going to be equal to the derivative of the Langevin function. So it will be nm Langevin function derivative with respect to alpha. This will be equal to delta MA divided by delta alpha, or I can write this as 2 delta MA over 2 delta alpha. It is net magnetization divided by 2 delta alpha. So I would see this. So I will obtain delta MA equals to nm, the derivative of the Langevin function, times delta alpha. So what is delta alpha? Alpha, remember, is mh over kbt. So delta alpha is basically for each sublattice m over kbt, magnetic moment per atom. So for a sublattice, let's say, we will have the change in the magnetic field acting on the a sublattice. So how much is the change in the magnetic field acting on the say a sublattice? We can calculate that. So this is for delta alpha I substitute, so L prime alpha and m, I substitute m over kbt, and the change in the magnetic field acting on the a sublattice. So this will be equal to nm square over kbt delta h on the a sublattice, derivative of the Langevin function at alpha 0. So this is at point alpha 0. Okay, so let's calculate the change in the magnetic field acting on the a sublattice. For t less than 0, I had a magnetic field, PHYS molecular field acting on the a sublattice, gamma mb. It was gamma mb. And for t greater than 0, acting on the a sublattice, I have the magnetic field H and then I have plus gamma mb minus delta mb. So this is the new field acting at t greater than 0. For the change in the field acting on the a sublattice, I will have for t greater than 0 minus for t less than 0. For t greater than 0, I have h plus gamma mb minus gamma delta mb. And for t less than 0, I had gamma mb. So basically, I find that the gamma mb's disappear, so it's going to be h minus gamma delta mb, which I have assumed to be equal to delta ma. So h minus gamma delta ma. So this will be the magnetic field acting on the a sublattice, the additional magnetic field. So I can substitute that for my delta ma expression. So I had the following result. Delta ma was equal to, let me copy this equation here, nm square over kbt. N was number of moments per volume. Langevin function at point alpha 0 times delta HA, and delta HA I have calculated nm square over kbt, Langevin function at alpha 0, H minus gamma times delta Ma, absolute value of gamma times delta Ma. So if I write this explicitly again, delta Ma This is again the so no need to use these absolute values actually. So let's just because delta MA is positive here. So H minus gamma delta MA. So here I have delta MA is equal to NM squared divided by KBT, Langevin function at alpha 0 times H minus N gamma M squared over KBT, Langevin function derivative at alpha 0 times delta MA. So if I put this into delta MA parentheses, I have delta MA parentheses 1 plus N gamma M squared over KBT, Langevin function derivative at alpha 0. And this is equal to NM squared over KBT, Langevin function derivative at alpha 0 multiplied by the magnetic field H. So what I would like to do is take this equation and multiply it by 2 kBt. So when I do that, I obtain delta MA, 2 delta MA, kBt plus N gamma M squared Langevin function derivative at alpha 0 is equal to 2NM squared Langevin function derivative at alpha 0 times H. And recall that the net magnetization we're looking for is 2 delta MA. So that was the result we had. So therefore, instead of this, I can write net magnetization, M net. So I have M as a function of H. Therefore, the longitudinal susceptibility can be written as M net magnetization I have in the field direction divided by the applied field. It is equal to 2NM squared Langevin function derivative at alpha 0 divided by kBt plus N gamma M squared Langevin function derivative at alpha 0. Or we can write this in Brillouin function, the same result if we use the Brillouin function, alpha 0 divided by kBt, the quantum version, and gamma M squared Brillouin function derivative at alpha 0. It's the same thing. So this is our main result for the longitudinal susceptibility. Let's use the Langevin version. And now we're going to talk about a remark here. What happens to this longitudinal susceptibility as temperature goes to 0? So what is the behavior as temperature goes to 0? What happens to the longitudinal susceptibility? Well, as the temperature goes to 0, alpha equals mh over kBt goes to infinity. So I have to look at the behavior of the Langevin function derivative. Let's look at the Langevin function, which is cotangent hyperbolic alpha minus 1 over alpha. If I look at the derivative of the Langevin function, I get 1 over alpha squared, and then I have the derivative of cotangent hyperbolic alpha with respect to alpha. So we have to find out this derivative. And I remember cotangent hyperbolic alpha is e to the alpha plus e to the minus alpha divided by e to the alpha minus e to the minus alpha. It's cosine hyperbolic alpha divided by sine hyperbolic alpha. So the derivative of cotangent hyperbolic alpha with respect to alpha will give me the derivative of the top, e to the alpha minus e to the minus alpha multiplied with the bottom minus the derivative of the bottom multiplied by the top divided by the bottom square, e to the alpha minus e to the minus alpha square. This gives us e to the 2 alpha plus e to the minus 2 alpha minus 2, then minus e to the 2 alpha minus e to the minus 2 alpha and minus 2 divided by e to the alpha minus e to the minus alpha square. You can see that these will cancel. So the answer is minus 4 e to the alpha minus e to the minus alpha square, which is basically minus 1 over sine hyperbolic alpha square. So that is the answer. Therefore, the derivative of the Langevin function with respect to alpha is 1 over alpha square minus 1 over sine hyperbolic alpha square. Okay, so let's take a look at what happens to this derivative as alpha goes to infinity. So the limit as alpha goes to infinity, I have 1 over alpha square minus 4 over e to the 2 alpha plus e to the minus 2 alpha minus 2. As alpha goes to infinity, this becomes 0. So here I have the limit as alpha goes to infinity minus 4 divided by, as alpha goes to infinity, this also goes to 0. Minus 4 divided by e to the 2 alpha minus 2. Minus 2 will be negligible, so this will become limit as alpha goes to infinity minus 4 e to the minus 2 alpha, and which will be equal to 0. So if I look at the limit as alpha goes to infinity, what happens to the longitudinal susceptibility? I can see that for the top 2nm square, the derivative is going as minus 4 e to the minus 2 alpha approaching 0 like this. And at the bottom I have kbt, and the next term will be n gamma m square, which is minus 4n gamma m square e to the minus 2 alpha. So now what I want to do is multiply the top and bottom with e to the 2 alpha. So what will that give me? So this is the limit as alpha goes to infinity 2nm square minus 4 divided by e to the 2 alpha kbt minus 4n gamma m square. Now since alpha is mh over kbt, kbt is mh over alpha, so the question is, how does this part behave? So for that part I have the limit as alpha goes to infinity e to the 2 alpha. It's since kbt is basically mh over alpha, so this will be e to the 2 alpha over alpha, which is an infinite over infinite limit. So this will be equal to limit alpha goes to infinity 2 e to the 2 alpha over 1, which is infinite. So this is going to infinity, and the rest is constant, therefore this answer is 0. So we find that as t goes to 0, the longitudinal susceptibility goes to 0. And I want to look at, in the second remark, the behavior of the longitudinal susceptibility as T approaches the nail temperature. We can follow the same calculations we did for Curie temperature for one sublattice. So following the same calculation for Tc for a sublattice, we can do the following. Alpha is equal to m PHYS molecular field acting on the a sublattice divided by kBt is going to be m gamma m divided by kBt. So this will give me m is equal to kBt over m gamma times alpha. So if I look at dmd alpha at the nail temperature, this must be equal to the initial slope of the Langevin curve, which is nm 1 over 3, so nm over 3. So this will be equal to kb Tn divided by m gamma. So I find that the nail temperature is capital N m square gamma divided by 3 times the Boltzmann constant. So if I look at the longitudinal susceptibility at T is equal to the nail temperature, I have 2nm square. At the nail temperature, the derivative of the Langevin function is 1 over 3 divided by kBTn nail temperature plus n gamma m squared over 3, and since n m squared gamma over 3 kb is the nail temperature, so this I'm going to substitute here, and basically I find that this is 2nm squared over 3 divided by twice kb nail temperature. And for nm squared over 3, I can write 3 kBTn over gamma. So this is going to be equal to, the 2's cancel, nm squared over 3 is 3 kBTn over gamma. And here I have kBTn. Oh, it's already 3, so it's kBTn over gamma. And these kBTNs will cancel, and I will find as my answer 1 over gamma. And 1 over gamma, if you go back to our transverse susceptibility, was the answer for the transverse susceptibility. So we're going to use that result, and we find that as T approaches the nail temperature, the transverse longitudinal susceptibility approaches the transverse susceptibility. So in summary, when we apply a magnetic field in the direction of the A sublattice, its magnetization increases, the B sublattice magnetization decreases. The net magnetization that we have in the A sublattice direction is twice delta Ma if we assume that the change in the magnetization of the B sublattice is the same, although it may not be exactly symmetric here. This is an assumption for simplification. And with that, if you look at the slope of the Langevin function multiplied by nm at point B, that must be equal to delta Ma over delta alpha. And we use the fact that alpha is mh over kBt and delta alpha is m over kBt delta Ha for the A sublattice, and then we calculate how much is the additional field we're applying on the A sublattice, which is H minus gamma delta MA. We calculate the longitudinal susceptibility in terms of the derivative of the Langevin function at alpha 0. Alpha 0 is when the applied magnetic field is 0. And if we look at the limit as t goes to 0, the Langevin function derivative is 1 over alpha square minus 1 over sine hyperbolic square alpha, and that is going to 0 as alpha goes to infinity. So we find that the longitudinal susceptibility goes to 0 as t goes to 0. At the Néel temperature, the slope of alpha equals mh over kBt gives us with the PHYS molecular field equal to gamma m is equal to kBt over m gamma alpha. So the PHYS theory and the Langevin theory slopes should be the same at the Curie temperature of the A sublattice, which is the Néel temperature of the antiferromagnet. We find that the longitudinal susceptibility at the Néel temperature is 1 over gamma, which is precisely the transverse susceptibility. So as t goes to Tn, the longitudinal susceptibility approaches the transverse susceptibility.